Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine looking up at the night sky and seeing a star just erupt.
Right.
For centuries, that's what astronomers saw. A nova would flare up, and we'd log it as this sudden, intense flash of light. It would get incredibly bright and then, slowly and predictably fade away.
That was the entire story.
Yeah.
A simple, impulsive explosion. That was the model.
But the actual moment, the blast itself, the shape of it unfolding in real time, that was always hidden from us. It was just a frustratingly blurry point of light.
It was a fundamental limitation.
Right.
I mean, we could measure the total light output perfectly. We could analyze the energy. We could clock the timing down to the second.
All the numbers.
But the actual physical movement of the material, the way it was flowing, whether there were lumps, how things were interacting, that was all just an inference. It was a guess based on computer models.
We just didn't have a telescope big enough to see the detail.
Exactly.
Yeah.
We lacked the resolving power to confirm the mechanics of the detonation itself.
Well, that era of inference is officially over. And for you, the curious learner, our mission today is to get right into this extraordinary scientific breakthrough, the first high-definition images of stellar explosions.
Yeah, this is huge.
We're going to break down the recent findings from a major study in Nature Astronomy and look at exactly how scientists managed to capture these stellar eruptions, these novae in really unprecedented detail.
And these images, they don't just, tweak the old models. They completely overturn the decades-old assumption that a nova is this single symmetrical puff of material.
It's not a simple balloon inflating.
Not at all. We now have visual proof of these incredibly complex non-uniform shapes. We're talking multidirectional jets. We're talking about dramatically delayed ejections. It's a whole new ballgame.
Okay, let's really unpack this, because to appreciate just how big of a loop this is, we need to understand the baseline. We need to get into the physics of what's actually exploding here.
All right, so we are focusing on novae. And it's so important to distinguish a nova from its more famous cousin, the supernova.
Right. Not the same thing at all.
Not even close. A supernova is the final catastrophic death of a massive star. It's a one-time event that completely destroys the star.
A nova, on the other hand, is a cyclical thing. It happens on a star that's, well, technically it's already dead, right?
That's the key. It's a surface-level explosion on a dead star that's locked into this fatal cosmic dance with a companion.
So if the star's already dead, what does that actually mean? What kind of dead star are we talking about here?
We're talking about a white dwarf. This is the remnant of a star like our own sun. After it exhausts its main nuclear fuel, it sheds its outer layers, and the core collapses down into this incredibly dense, super hot object.
So you've got something with the mass of the sun squeezed into the size of, what, the Earth?
About the size of the Earth, yeah. It can have up to 1.4 times the mass of the sun crammed into that tiny volume. And that density, that concentration of mass, is what gives it this immense gravitational pull.
And it's not held up by normal pressure like a regular star. It's something else, something exotic.
Precisely. Its structure is maintained by something called electron degeneracy pressure. It's a quantum mechanical effect. The electrons are packed in so tightly that they physically resist being compressed any further.
So it's stable. It's basically an inert stellar core just sitting there.
It is. It's stable and inert, but its immense gravity is still very, very active. And that's what sets the stage for the explosion. It needs a trigger.
And that trigger comes from its, let's say, unfortunate companion star.
Exactly. This white dwarf is almost always part of a close binary system, and it acts like a cosmic thief, just pulling material, mostly hydrogen and helium, off its companion.
It's literally stealing fuel.
It is. This stolen material forms a turbulent, swirling cloud around the white dwarf called an accretion disk. And from there, it spirals down and piles up, forming this shallow, super dense layer on the white dwarf's surface.
Okay, so you have this dead quantum-supported core, and it's now covered in a fresh layer of highly compressed hydrogen. What flips the switch? What turns that into a city-sized hydrogen bomb?
Well, this is where the specific physics gets really interesting. As that hydrogen layer piles up, the immense gravity from the white dwarf creates incredible pressure and heat at the bottom of that layer.
It's being crushed.
Crushed and cooked. The white dwarf itself is extremely hot, maybe 100 million Kelvin. So the base of this new hydrogen envelope heats up very quickly.
But the core itself isn't doing any fusion anymore. It's just a hot rock, essentially.
That's right. The core is inert. But here's the key to the explosion. That hydrogen layer is supported by the same degeneracy pressure as the core. And degenerate matter has this weird property where its temperature can skyrocket without its pressure immediately increasing to match.
So in a normal gas, if you heat it up, it expands and cools.
Right. It's a natural thermostat.
But that doesn't happen here.
It doesn't happen here. The temperature just keeps climbing and climbing. It's a runaway heating process. And when it hits the critical threshold, somewhere around 10 to 20 million Kelvin, that hydrogen suddenly ignites.
And we're not talking about a slow burn.
Oh no. It's a catastrophic runaway thermonuclear reaction. The CNO cycle carbon-nitrogen-oxygen fusion kicks in violently, releasing a massive amount of energy that finally overcomes the star's gravity. It blasts that entire accumulated layer into space at thousands of kilometers per second.
And that's the flash. That's the nova we see.
That's the nova. The star temporarily brightens by many, many orders of magnitude.
An incredible blast. And yet, for all of history, we could only interpret it. The material expands so fast that even our best single telescopes just saw it as that single, smooth, unresolved point of light.
That was the historical observation challenge.
Yeah.
Because they're so far away, even something expanding at, say, 5,000 kilometers per second still looks like a tiny, slowly growing blob. We knew mass was being ejected, but we couldn't resolve the geometry.
The shape, the direction, whether there were jets or clumps.
All of that was hidden in those crucial first few hours and days.
So because the geometry was hidden, the physics of the explosion was, well, it was based on the assumption that it was symmetrical, right? Like a perfectly inflated balloon.
Exactly. And that created a huge knowledge gap. I mean, understanding the geometry is everything because it dictates how the ejected material interacts with itself.
If it's a smooth sphere, the physics is pretty straightforward.
Relatively simple, yes. But if you have multiple outflows or lumpy bits or directed jets, then they're going to crash into each other.
And that's where things get interesting.
That's where you get intense shock waves. And those shock waves are where the highest energy physics, the particle acceleration, takes place. Before this study, the true complexity of those shock-powered processes was a complete mystery. We were modeling simple physics because we couldn't see the complex reality.
So given this massive barrier, this fundamental limit of distance and resolution, what was the breakthrough? How did we finally see the physics as it happened?
The answer is a really advanced technique called long baseline optical interferometry.
It sounds incredibly complex, but the basic idea is a clever way to cheat the system, right? To get around the problem of building impossibly large telescopes.
That's a perfect way to describe it. Look, if you want higher resolution, the ability to see finer details, you just need a bigger mirror, a bigger aperture.
But building a single mirror beyond, 8 or 10 meters in diameter is just an immense engineering challenge.
Immensely complex and incredibly expensive.
Yeah.
So interferometry solves this by combining the light waves from multiple physically separate telescopes.
So instead of one giant 100-meter mirror, you can have, say, a handful of smaller mirrors spread out over 100 meters.
Exactly. And the combined system acts as if it were a single giant telescope whose diameter is equal to the maximum distance between any two of the smaller ones.
It creates a synthetic aperture.
And that's the term. The resolution you get is dictated by that longest baseline, not the size of the individual mirrors. And this lets astronomers achieve resolutions equivalent to a mirror hundreds of meters across. It's just phenomenal.
And we should stress, this isn't some brand new, untested idea. This is the same powerful technique that was crucial for the Event Horizon Telescope project.
The one that gave us the first ever image of a black hole shadow.
Right. So when we're talking about resolving power, this is the absolute cutting edge.
It really is. And the specific facility that pulled off this NOVA breakthrough is the Center for High Angular Resolution Astronomy, the CHARA Array up in California.
Tell us about that setup, because it's at a really historic site, but the tech itself is, it's borderline science fiction.
It's a wonderful marriage of history and the future. The CHARA Array is at the Mount Wilson Observatory in the San Gabriel Mountains, which is, famous for Edwin Hubble's work discovering the expansion of the universe.
A legendary place in astronomy.
Absolutely. And the array itself consists of 6 one-meter telescopes. These 6 telescopes are arranged very precisely along 3 arms in a big Y shape. The longest distance between any two of them is 330 meters.
So you're getting the resolving power of a 330-meter telescope. That's just, it's mind-boggling. But it requires this almost impossible feat of engineering. You have to get the light from all 6 separate telescopes to arrive at the central lab at the exact same time.
Down to fractions of a wavelength of light.
How do you even do that?
That is the core technical challenge. It's called maintaining coherence. Light travels at a finite speed, so you have to compensate for the different distances. CHARA uses these incredibly precise systems of movable mirrors on railway tracks. They're called delay lines.
And they're all inside sealed vacuum pipes, right, to keep the atmosphere from messing with the light.
Correct. The light from each telescope is beamed into these vacuum pipes, and these delay lines physically move back and forth, constantly adjusting the path length of the light to make sure all 6 beams are perfectly synchronized when they meet and interfere in the central lab.
The precision must be on the order of nanometers.
It is. They have to align the light paths with unbelievable accuracy to track the interference pattern, the fringes, and build up a coherent image. And it's all happening in real time. Because the Earth is rotating, the object is moving across the sky, those path lengths are constantly changing.
That level of coordination is already a huge feat. But for something like a nova, you can plan for years to image a static target like a black hole. A nova just appears.
And that's what makes this so impressive. It requires immense operational flexibility. A nova can brighten dramatically in less than a day. The team has to be able to drop everything, pivot the entire array, all 6 telescopes, all the optics, all the synchronization, and lock onto this new target immediately.
It's high-stakes, rapid response science.
It really is.
Yeah.
But the visual data from CHARA, as powerful as it was only half the picture. They used a really smart complementary approach to double-check their work.
So they weren't just relying on the images alone.
No. The sharp images from the interferometry told them the shape and the structure. But they complemented that data with spectra gathered from major observatories like Gemini.
And the spectra, that's like the chemical fingerprint of the gas.
Yeah, exactly.
Yep.
It tells you its velocity, its density, its temperature, its chemical composition. All the physics.
So you have the geometry from one instrument and the physics from another, and you can marry them up.
And this is where their confidence just soared. The study found what they called a powerful one-to-one confirmation as soon as a new high-velocity feature appeared in the spectra.
Meaning a burst of fast-moving gas or a strong collision?
That spectroscopic signal lined up perfectly with a new structure, a new lump or jet that simultaneously appeared in the interferometric images.
That's the smoking gun. It proves you're not just seeing some kind of optical artifact. You're visually confirming the physics.
It validated the entire process. One of the co-authors called it an extraordinary leap forward, and he's not wrong. We are now literally watching the material as it's blasted into space and connecting that directly to the physics of how it's happening. We've gone from theorizing about how shock waves form to directly observing them form.
And what that new window immediately showed was that the simple spherical model of a nova is, well, it's just wrong.
It's completely insufficient.
The team managed to image 2 novae that erupted in 2021, and they couldn't have been more different from each other. That variability is really the heart of this whole discovery.
Absolutely. The contrast between these 2 novae, V174 Hercules and V1405 Cassiopeia, is the direct evidence that's forcing us to rewrite the textbooks. We're seeing this incredible variety of ejection pathways.
Which proves that the final shape isn't just about the energy of the blast.
Right. It must be highly dependent on other factors, like the white dwarf's rotation or its magnetic field or the shape of the material it's stealing.
Okay, let's get into the first case. Nova V1674 Hercules. The sources describe this one as one of the fastest stellar explosions ever recorded. What do we mean by fast?
We mean blindingly fast. V1C74 Hercules peaked in brightness and then faded away in just a few days.
Just days.
Just a few days. A more typical nova might take weeks or even months to go through its whole cycle. So this rapid evolution meant that the crucial early stages, the initial ejection of material, were all compressed into this tiny observational window.
Which makes the fact that they caught it with CHARA even more incredible.
It's a huge achievement. And what they saw in this first couple of days, the geometry was stunningly asymmetrical.
Not a sphere.
Not even close to a sphere. The images, taken just 2.2 and 3.2 days after the explosion, revealed the immediate formation of 2 distinct perpendicular outflows of gas.
Perpendicular, so not just 2 jets shooting out from the poles, but 2 sets of jets at right angles to each other.
That's what the data shows. We're talking about high-speed jets of material shooting out almost at right angles, It's an incredibly complex shape to form so quickly.
That implies the explosion's engine isn't uniform at all. What kind of physics could possibly drive flows like that?
That's the million-dollar question now, and it's probably tied to the system's rotation and magnetic fields. A rapidly spinning white dwarf can easily form a bipolar outflow, two jets shooting from the poles.
Right, that makes sense. The path of least resistance.
But perpendicular flows suggests something even more complex is going on. Maybe a pre-existing structure that the blast is hitting, or perhaps a rapidly tumbling or tilted magnetic field that's channeling the plasma in multiple directions at once.
So this is direct visual evidence of multiple interacting ejections, not one single puff.
That's the takeaway. And what's critical is that this complex geometry immediately explained the high-energy data they were seeing at the same time.
The gamma rays.
The gamma rays. The images from CHARA showed these fast-moving jets colliding with slower-moving gas that was probably ejected just a little bit earlier. This violent collision is the perfect setup for generating intense shock waves.
And we now know those shock waves are the source of the gamma rays that NASA's Fermi Space Telescope saw.
It was direct, irrefutable proof. The geometric complexity is driving the high-energy physics.
Okay, so that's one star that just rushed through its explosion with this spectacular jet-driven chaos. But then we look at the other one, NOVA V1405 Cassiopeia, and it seems to be operating on a totally different schedule.
V1405 Cassiopeia was the polar opposite in many ways. It evolved much more slowly, which isn't unheard of. But the central surprise here was a clear, dramatic, physical delay. This nova showed the first clear evidence of a delayed expulsion.
A delay? What does that mean? The explosion happened, but the material didn't leave.
Essentially, yes. The star held onto its outer layer's material for more than 50 days.
50. So for almost 2 months, the thermonuclear runaway had already happened on the surface, but the material was just stuck there.
That's right. The energy was generated, but the stellar envelope didn't fully disperse. It was contained somehow.
That's incredible. I mean, the pressure from a runaway thermal pulse should be enormous and immediate. What could possibly hold it in for 50 days?
It suggests there was some powerful confining mechanism, perhaps an incredibly strong and compressed magnetic field acting like a cage, trapping the plasma, or maybe an unusually dense initial envelope that needed a lot more sustained energy to finally overcome the star's gravity.
Whatever the cause, the consequences when that containment finally failed must have been spectacular.
They were. When the material was finally expelled after that 50-day confinement, it erupted violently. This triggered new, incredibly intense shocks. It's like a spring that's been compressed for 2 months and is suddenly released.
And I'm guessing Fermi saw a burst of gamma rays from this one, too.
A huge burst of gamma rays, yeah, which provided even more support for this shock-driven model of high-energy emission.
So what's fascinating here is the sheer variability. You look at just 2 events, and you get one that's immediate perpendicular jets, and another that's a 50-day magnetic cage scenario.
It completely shatters the idea of a standard nova. It tells us that the local environment, the white dwarf's magnetic field, its spin, the density of the material it's stealing, all of that dictates the outcome. The geometry is everything, and the geometry is wildly diverse.
So we have the visual proof of the geometry. We have the timeline of the ejection. Now we have to connect the dots. Why does seeing these structural details, the perpendicular jets, the 50-day delay, why does that matter so much to the broader field of high-energy astrophysics?
Because it directly solves a major puzzle from the last decade, which is, where are all these high-energy gamma rays in our galaxy coming from?
We knew novae were one of the sources.
Right. Before CHARA, NASA's Fermi Large Area Telescope had detected GeV emission, that's gigaelectron-volt gamma rays, from more than 20 novae. This established them as significant galactic gamma ray factories.
We knew the factory existed, but we didn't know how the machinery inside actually worked. We assumed it was shock waves, but that was just a theory.
It was a very strong theory, but it was still a theory. These new images provide the direct proof. They allow us to definitively tie the gamma rays seen by Fermi not to the initial flash, but directly to those colliding outflows.
The visual structures are the engines creating the high-energy radiation.
Precisely. It's a remarkable piece of validation. If novae were truly spherical, those shock waves would dissipate quickly and symmetrically. You probably wouldn't get such intense gamma rays. It's the fact that the ejecta are lumpy and messy and colliding that creates the perfect conditions for particle acceleration.
This elevates novae from just being, pretty fireworks in the galaxy
to being, as the source material calls them, laboratories for extreme physics. This is where we get to study how energy is transferred in the cosmos in a real-world setting.
I love that phrase. Let's dig into that. What do we mean when we say novae are labs for studying shock physics and particle acceleration? What's actually happening in those collisions?
We're talking about natural particle accelerators that are far more powerful than anything we could build on Earth. The shock waves from these collisions are incredibly efficient at scooping up charged particles, protons, electrons, and accelerating them to near the speed of light.
And this happens through a process called diffusive shock acceleration, or the Fermi mechanism.
That's the one. The basic idea is that particles get trapped near the shock front and bounce back and forth across it repeatedly. It's like a cosmic pinball game.
And with each bounce, they gain energy.
They get a kick of energy with every single pass. And they do this over and over, rapidly accelerating until they have enough energy to produce gamma rays, which are the highest energy form of light.
And because CHARA gives us the precise visual of when the collisions happen and what the shape of the colliding material is, we can now test our models of that acceleration process with real data.
That's the key. Before, these models were mostly tested in much bigger, much messier systems, like supernova remnants. Novae are smaller, they happen much more frequently in our own galaxy, and they evolve faster, which makes them fantastic accessible laboratories.
So this isn't just about understanding one type of stellar explosion. It's about fundamental physics.
It's about the origin of cosmic rays. It's about how particles get energized throughout the universe. And it all comes back to challenging that long-held view that nova eruptions are simple, single events. That model is dead.
So if we connect this to the bigger picture, this means we can finally draw a direct, cohesive line all the way from the nuclear reactions on the star's surface
to the geometry of the material flows that result from it.
And finally to the high-energy gamma rays that are produced by those flows. It's the whole chain of events, observed from start to finish.
Exactly. It's linking the microphysics of the surface to the macrophysics of the shock waves and the ultra-high energy output. This reshapes our models of how even relatively small stellar events like novae contribute to the energetic budget of the Milky Way.
It's taken hypothesis and turning it into observed, tested reality. Knowing the gamma rays come from shocks is one thing, but actually seeing the messy jets and delayed explosions that create those shocks, that's the ultimate confirmation.
And it means we can start asking much more specific questions. We can use the geometry to infer things about the white dwarf's rotation speed, its magnetic field, and the accretion rate, all of which drive these dramatic and varied explosions.
This has been incredible, going from the weirdness of electron degeneracy pressure all the way to aligning light beams with nanometer precision. We've gone from seeing novae as these simple flashes to understanding them as these complex, geometrically rich events.
You have the immediate perpendicular jets of V1674 Hercules on one hand.
And on the other, you have the dramatic 50-day delayed eruption of V1405 Cassiopeia, just completely different beasts.
And we have to remember, this is just the beginning. The lead author of the study said as much. The fact that they found such complex and varied shapes in just their first two detailed observations suggests the field is wide open.
There's probably a whole zoo of other shapes and behaviors out there.
A whole zoo. With more observations, scientists can start answering the really big questions about the diverse ways stars shed their mass and influence the universe around them.
The era of the unresolved point of light is definitely over. Novae, which we once thought were pretty straightforward, are now revealed to be so much richer and more fascinating than we ever imagined. And that fascination really leads us to our final thought for you, the learner.
Think about it. We observed two novae, just two, and they displayed wildly different behaviors. One was fast, with perpendicular flows likely driven by rotation or magnetism.
And the other was a slow burn, a 50-day delay, probably caused by some kind of magnetic cage.
The fact that you see such extreme variability in a statistical sample of two, well, that suggests that the cosmos is holding a huge number of geometrical surprises for us.
So if the universe showed us two fundamentally different ways for a star to explode right out of the gate, what other unexpected, unseen, and maybe even bizarre mechanisms are out there?
Could we see corkscrewing jets? Or episodic stuttering bursts? Or maybe three-way collisions from a truly chaotic magnetic field we just don't know?
The stellar physics textbooks are clearly due for a major rewrite, and we'll be watching the skies right alongside the CHARA team to find out what new chapter they uncover next.